Yes, students, good morning. In continuation with the video lectures based on Chapter 9, Class 11th Physics, Chapter 9, Mechanical Properties of Solids, today we are going to start with new topic, that is Poisson's ratio. And dear students, these topics are not according to the curriculum of 2021 of physics, but in spite of the fact I was discussing it for your knowledge. So the Poisson's ratio we will discuss, as we had discussed in the mechanical properties of solids, that suppose there is a rigid body, and if on that rigid body a force is applied, if a force is applied on this rigid body, then what will happen? If a tensile force is applied or tensile stress is given, then we had studied that its length is going to be increased and the strain produced in the rigid body is called as longitudinal strain. But here we should have to mark one point, that if the length of the rod or if the length of the rigid body is going to be increased, then obviously there is change in its diameter also, its cross sectional area also reduces. But for our discussion we are not using the change in area or change in diameter, but for Poisson was the scientist, he had studied about the relation between the change in diameter and change in length, and the ratio he had given called as the Poisson's ratio. So let us start with Poisson's ratio. Suppose there is a body, and a tensile force is being applied on this body, and suppose the length of the body is L, then its length is being increased with a value that is called as delta L. Its length is increased with its value called delta L. But what with its diameter? Suppose D is the initial diameter before the application of the force. D is the initial diameter, then its diameter also going to be reduced. Its diameter also going to be reduced. Its diameter is reduced, and this diameter will become what? D minus delta D. This diameter is D minus delta D, and the reduction in the diameter, that is equal to delta D. This is equal to delta D. So dear students, the strain produced in length, strain produced in length is called as longitudinal strain. That strain is called as longitudinal strain, and longitudinal strain, you know that longitudinal strain, this longitudinal strain is given by delta L, change in length upon original length, and strain produced in diameter, strain produced in diameter is called as lateral strain. That strain is called as lateral strain, and lateral strain is given as delta D upon D. So these are the two strains which is being observed when a tensile force is either tensile or compressive also. In compressive, what will happen? The diameter will increase. So I am here taking the case only for the tensile stress, and or when the force, extension force is applied on the rigid body, then here the ratio of lateral strain to longitudinal strain, ratio of ratio of lateral strain to longitudinal strain. This ratio is called as Poisson's ratio. This ratio is called as Poisson's ratio. So Poisson's ratio sigma can be given as delta D upon delta L upon L, or you can write it as delta D into L upon D into delta L, or you can say that delta D upon delta L into L upon D, and there is a negative sign placed over here. And why this negative sign? This negative sign indicates that the longitudinal strain and the lateral strain are of opposite sense, because one is increasing and other is decreasing. The relative change between longitudinal strain and lateral strain is of opposite sense, so we place a negative sign over here. So negative sign indicates that lateral strain and longitudinal strain are of opposite sense. What does negative sign indicates? Negative sign indicates that lateral strain and longitudinal strain are of opposite sense. Look at here. Here longitudinal strain, the length is increasing but the diameter is decreasing. So we had placed a negative sign over here. So dear students, this is all about the Poisson's ratio. Now we will discuss about certain factors which influence the elasticity of material. So what are the factors on which elasticity of the materials depend? So dear students, now we are going to discuss the factors on which the elasticity of material depends. Means what are the factors which are capable of reducing or increasing the elasticity of a material. Means with what factors the elasticity of a material depends. The first factor is hammering or rolling. What does it mean, beta? Hammering or rolling? It means to say that if there is a body and what you are doing, you are again and again putting stress over that body or again and again hammering that body, then obviously the body is going to lose its elasticity. Or you are rolling the body. Suppose there is a body and you are making roll of that body, means you are folding that rigid body, and due to folding that rigid body also the elasticity of again and again you are folding that body, then elasticity of the body is going to be decreased. Second one is annealing. Breaking into crystals. Means if on a given body or on a rigid body you are applying such a force or such a stress that by that stress the rigid body is going to be break down into its crystal form. By breaking a solid into its crystal form, the elasticity of the rigid body is going to be decreased. The third one is adding impurity. Adding impurity to the body. Yes, students, you can increase or decrease the elasticity of a material or elasticity of a rigid body or a solid body by mixing impurity with that body. So it has been observed that various alloys has more elasticity due to mixing of two elements or mixing of two materials. The elasticity is going to be suffered of that material. So mixing of impurity is another technique to increase or decrease the elasticity of a given material. And fourth one is temperature. Temperature is a factor. With increase or decrease the temperature of a given body, with increase or decrease we can change the elasticity of the solid. Suppose you are heating, you are increasing the temperature of a solid body, then by increasing the temperature it will become less elastic, or elasticity will decrease, and on decreasing the temperature, the temperature increases, elasticity decreases, and temperature decreases, elasticity increases. With decrease in temperature you can increase the elasticity of the material. So these are the various factors over which the elasticity of a material depends. Now we are going to discuss another thing, that is elastic after effect and elastic fatigue. Elastic after effect. Elastic after effect. What does it mean by elastic after effect? Suppose I am taking an example. Suppose there is a rod and you had applied a force. Since it is an elastic material, means on removal of this force, the body regain its shape, but there is a time delay in regaining the shape. So whatever the time delay by an elastic body to regain itself, the time delay by an elastic body to regain its shape is called as elastic after effect. Time delay by an elastic body to regain its shape is called elastic after effect. That is called elastic after effect. Whatever the time delay by a rigid body to regain itself, its original shape or original form, that time delay is called elastic after effect. And the another thing is elastic fatigue. Dear students, you had heard the term fatigueness. Fatigueness means thakawat. Fatigueness means, have you ever experienced that again and again working by your muscles, the muscles does not get proper oxygen supply and starts doing anaerobic respiration, and due to the less supply of oxygen, due to anaerobic respiration, the lactic acid is being produced by the muscles, and it is the cause of the muscle fatigueness. And you usually use the term that my muscle got fatigued. After a heavy exercise, you used to say this term that my muscles got fatigued. So similarly, when there is a body, when there is a elastic body, and when again and again a stress is being applied on that elastic body, suppose this is a body and again you are stretching this body, then it becomes elastic fatigue, means it loses its elasticity, and after that it will be breakdown. So this condition is called as elastic fatigueness. Elastic fatigueness you had observed in cranes. In cranes, when the rope of the cranes are used to lift the heavy weight, again and again the rope is going to be breakdown. It is due to the elastic fatigueness of the rope of the crane. Similarly, when bridges got old and again vehicles are traveling from the bridge, the iron bars which are attached in the bridge gets elastic fatigue and it starts breaking. So this concept is called as elastic fatigueness. Okay, so these are the things which are related to the elasticity. Now we are going to discuss about the energy stored in an elastic body. Yes, students. Now we are going to discuss about energy stored in a deformed bodies. How energy is being stored in a deformed body. Look at here. Suppose this is a rigid body and on this rigid body you are applying a force. If a force is being applied on this rigid body, then what will happen? As you are going to suppose this is a rigid body, and as you are going to apply force on this rigid body, what will happen? The interatomic forces come into play. Interatomic forces. That interatomic forces come into play, and this interatomic forces, this interatomic forces which are existing due to the applied force, that interatomic forces tries to maintain the body in its original shape. That interatomic forces tries to maintain the body into its original shape. So a work is being done, or whatever the work you had done in stretching the body, that energy is being stored in the body, and we have to calculate that energy is stored in the deformed body. Suppose I am taking an example. Suppose this is a chalk and you are lifting the chalk to this height. So you had done work in lifting the chalk to a certain height, and whatever the work you had done in lifting the chalk to a certain height, that work done is stored in that chalk up to that at that height. Now if the chalk falls from that height, it will do some work. So similarly, whatever the force you had applied in stretching the body, that force is going to be, that work done is going to be stored as an energy, because due to the application of this force, the body is going to be deformed by a distance of delta L. Delta L means certain amount of work you had done, and that work done is being stored as energy, and we have to calculate this energy. Now listen, students. Initially the force on the rigid body, initially the force on the rigid body is 0, and after time t, when force F is applied, the force is F. After certain time, the force is equal to F. So now here we have to calculate the average force. So average force acting on the average force acting on the rigid body, it can be given as F average is equal to 0 plus F divided by 2, that is equal to F by 2. That is the average force acting on the rigid body. Now we had got the force, average force. So work done in stretching the body by delta L. What is the work done in stretching the body by delta L? So W is equal to, you can write W is equal to F average into delta L, and it can be written as F by 2 into delta L. F by 2 into delta L. Now this work done, whatever the work you had done, that work done is energy, stored as energy in the rigid body. So energy stored in the body, that energy stored, I am representing it by U. U is equal to W is equal to F into delta L divided by 2. Now we have to calculate energy density. We have to find out delta L. We have to find out the energy density, and energy density is what? Energy density is equal to energy per unit volume. As you know that mass density is what? Mass per unit volume. Similarly, energy density is energy per unit volume. So energy density you have to calculate, and I am denoting it by a small u, energy density. And energy density is what? U upon volume. And you have to calculate U, you had calculated, that is F into delta L upon 2. And if I am saying about volume, the volume, it means to say that length L and area of cross section A. Area of cross section A and length L. So A into L is the volume. So 2AL into AL. 2AL into AL. And look at here. You can write it as F 1 by 2 into F upon A into delta L upon L into AL. Okay, students? Now I am rubbing here. Look at here. Now energy density U, and it can be given as what? It can be given as 1 by 2 into 1 by 2 into stress into strain. 1 by 2 stress into strain, because you had divided it by volume, multiplied it with volume. Clear? So now, since it is only energy, not energy density. It is energy density, small u, or energy density. Now here you are calculating U, only energy. I have defined here only energy density. U is equal to, now this is only energy U. Now strain into volume. Now dividing volume with energy divided by volume. energy upon volume, and energy upon volume we had discussed at as a small u, and it is equal to 1 by 2 into stress into strain. Okay students, so this is the expression for energy density. Now we are going to discuss about energy density in terms of Young's modulus. So you know that 1 by 2, it can be written as Young's modulus into strain square, because as you know that Young's modulus is what? Young's modulus is equal to stress upon a strain. Young's modulus is equal to stress upon a strain, and a strain to a strain cancel out, and it will become 1 by 2 stress into a strain. So energy density U, it can be given by this also. Energy density U can be this by this expression also, 1 by 2 Young's modulus into strain square. So this is about the energy stored in deformed bodies when you are using the deforming force on the body. Now dear students, we are going to solve two numericals based on this. Yes students, here look at the question. There are two wires A and B, and a rod is attached with the given wire at its two ends. The length of the rod is 1.05 meter, and here at this end F1 is applied and at this end F2 is applied. So first of all we have to calculate the distance x for where mass m, that is m is equal to mg, is loaded such that the strain and stress in both the wires are equal. So we have to calculate the distance x for which the stress and strain are equal. And another thing, so first of all we will calculate about the stress when what is the value of x for which the stress produced in both the wires will be equal, and after that we will calculate about the strain. What will be the strain, what will be the position of x for which the strain produced in both the wires will be equal. So first of all we will calculate the for equal stress. So for equal stress produced in wire A is equal to stress produced in wire B. Stress in wire A is equal to stress in wire B, and it is equal to F1 upon A1, and that is equal to F2 upon A2. Now from here we can find out F1 upon F2 is equal to A1 upon A2. F1 upon F2, that is equal to A1 upon A2, and from here we will find the value of F1 upon F2. So F1 upon F2, and it is equal to 1 into 10 to the power minus 6 meter square upon 2 into 10 to the power minus 6 meter square. It will be cancelled out, and it is equal to 1.2. F1 upon F2 is equal to 1 upon 2. Now look at here students, we have to, since it is in rotational equilibrium, since the body is in rotational equilibrium, so moment about the mass m must be same. So we can say that moment about mass m. So F1 into x is equal to, this distance will be y is equal to what? Y is equal to 1.05 minus x. So f2 into 1.05 minus x. Now from here we want to calculate the value of x. So here f1 upon f2 is equal to 1.05 minus x upon x. And look at here, students, we can write f1 upon f2, it is equal to 1.05 upon x minus 1, and the ratio of 1 upon 2 is 1 by 2, plus 1 is equal to 1.05 upon x, and it is equal to what? It is equal to 3 by 2 is equal to I am writing here 3 by 2 is equal to 1.05 upon x, or x is equal to 1.05 into 2 divided by 3. X is equal to 1.05 into 2 divided by 3, and it is equal to 0.7 meter. X is equal to 0.7 meter. This is the value of x. So for equal stress we had calculated the value of, for equal stress we had calculated the value of x. Now for equal strain we have to calculate the value of x. Now we have to calculate the value of x for equal strain. Second one, for equal strain, and for equal strain we have to calculate the value of x. So strain in A is equal to strain in B. So you know that Young's modulus is equal to what? Stress upon strain. So strain can be written in terms of Young's modulus stress upon Young's modulus. So for still wire, that is A, for still wire, that is wire A, for still wire we have to calculate, and for still wire if you have to calculate the strain, then strain in still wire, strain in still wire, that is equal to what? F1 upon A1 divided by Y1, Young's modulus for. So F1 for still is given F1 you are not knowing, na? F1 upon F2 you are knowing the ratio. So F1 upon area of still 1.1 into 10 to the power minus 6 into Young's modulus 2 into 10 to the power 11, and it is equal to F1 upon 2 into 10 to the power 5. F1 upon 2 into 10 to the power 5. And similarly, you have to calculate strain in case of second aluminum, that is F2 upon A2 Y2, and Y2 you are knowing. So F2 A2 it is given 2 into 10 to the power minus 6 into 7 into 10 to the power 10, and from here F2 you can calculate 14 into 10 to the power 4, 14 into 10 to the power 4. So strain should be equal. For equal strain, so we can say that F1 upon 2 into 10 to the power 5, that is equal to F1 into 10 to the power 5, that is equal to 40 F2 upon 14 into 10 to the power 4, and F1 upon F2. You had got the ratio F1 upon F2. That is equal to 2 into 10 to the power 5 upon 14 into 10 to the power 4. Now, you had calculated the value of F1 upon F2, that is equal to F1 upon F2 1.05 minus X, 1.05 minus X upon X. From principle of moment, we had calculated the value 1.05 upon minus X upon X, and this value is equal to 2 into 10 to the power 5 upon 14 into 10 to the power 4, and it is equal to 10, and it is equal to, that is equal to 10 upon 7, 10 upon 7, and on calculating it, we will get the value of X 0.43 meter. X is equal to 0.43 meter. We will get the value of X as 0.43 meter. So in both the cases, we had calculated the value of stress and strain, and for which what will be the position of the mass M in for getting equal stress and strain. So that's all for today video, and now in the next video we are going to start our new chapter, that is mechanical properties of fluids. Thank you students, have a nice day.